Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, as you know that since the previous lectures we have been talking on carbohydrates. We have conducted 2 lectures on carbohydrates and this is the 3rd lecture on carbohydrates. Dear friends, for this very discussion we have again with us in our studios Dr. K.K. Arora. Dr. K.K. Arora is Associate Professor in Department of Chemistry, Zakir Hussain, Delhi College, University of Delhi. We have tried to understand the various aspects of carbohydrates. I believe that this session is also going to be one of the finest sessions as we are going to understand more about carbohydrates through Dr. K.K. Arora. So, without wasting any time, I would like to welcome our guest, Dr. K.K. Arora. Dr. Arora, welcome to the ETC lecture.
Thank you.
So, we are going to understand more about carbohydrates. So, what else do we have in this session today on carbohydrates?
Hello viewers. Our today's session has been planned like this, that first we will briefly review what we had done in our previous session. Then we will talk about another method of configurational nomenclature that is called trio and erythro. We had already discussed a method of nomenclature that is capital D and capital L. Then we shall talk about the cyclic structure of D plus glucose. In our previous session we had discussed that how the open chain structure of D plus glucose was arrived at. Then how to draw these molecules. There is one projection formula given by Haworth, we call it as Haworth projection for the cyclic structure in carbohydrates. Then we will see that what is actually the conformation, because the cyclic compounds they exist in chair or board conformation. For these molecules we have discussed that chair conformation is more stable, and we shall discuss conformational representation for D plus glucopyranose. We shall also take up the cyclic structure of fructose. Then we will discuss one property that is called mutarotation and we will take its mechanism. Then how these monosaccharides are represented in different ways in open chain structures, and finally we will talk about glycosides and summarize our today's work. Now till now we have discussed that glucose is a molecule which consists of 6 carbons. These 6 carbons are attached to each other forming a straight chain. One of the carbon is present as aldehydic functional group, which is obviously the carbon number 1, and all remaining 5 carbons contain 1 hydroxyl each. Now if this is the structure, then these 4 carbons which are starred here, they are asymmetric carbon atoms, means this can have 4 asymmetric carbon atoms. So total number of possible stereoisomers for this molecule is 16, and out of those 16 stereoisomers it is only one configuration that represents D plus glucose. In our previous session we had seen that how Fischer arrived at a particular configuration for D plus glucose, which is like this, that hydroxyl at carbon number 2 is placed on the right side, then at 3 on the left, then 4 and 5 on the right side. So this is the configuration representing the wedge formula for D plus glucose. Then Fischer gave another method for drawing these configurations as a planar representation. We call it as Fischer's representation. According to that we also call it as Fischer's formula. So D plus glucose can be written like this in their Fischer projection. You must have studied earlier in stereochemistry that in Fischer projection one cross represents one carbon at the center and then other 4 are substituents at that asymmetric carbon atom. The groups which are written on the horizontal line are towards the viewer, and those groups on the vertical line are going away from the viewer. So here there are 4 asymmetric carbon atoms, carbon number 2, 3, 4 and 5, and these lines represents how the hydroxyls are placed, whether on the right side or on the left side. Similarly, the configuration for fructose was also determined. Fructose was also found to be a molecule with 6 carbons in straight chain, but it is a keto sugar and carbonyl group is present at carbon number 2. all other 5 carbons have 1 hydroxyl each, and molecule has got 3 asymmetric carbon atoms. So, 8 isomers are possible, and out of those 8 possible configuration, the one that actually represents D minus fructose is this. This is also written in the Fisher's projection. So, up to this point we had discussed in our previous sessions. Now, when the configuration for this glucose or fructose or some other monosaccharides were determined, then a new method was used to give the name to configuration of molecules, and it was based on the configuration of 2 sugars which are of 4 carbon, and they are named as triose and erythrose. This is erythrose, and these are 2 isomers for erythrose. This is D-erythrose, this lowermost asymmetric carbon atom having hydroxyl on the right side, and its mirror image L-erythrose having this hydroxyl on the left side, and this is triose with this hydroxyl on the lowermost asymmetric carbon atom on the right side, and this with the hydroxyl group on the left hand side. Now, we find that in erythrose, when it is written in the Fisher projection, 2 similar groups, that is hydroxyl groups or hydrogens, they are on the same side, whereas in triose they are across. So, based on this, if any other molecule which has got 2 asymmetric carbon atom and at least there is one common substituent on these 2 carbons, then according to that those isomers are written either as trio or erythro, depending upon that their groups are in cross fashion or on the same side. So, erythro means diastereoisomer with the similar groups on the same side, and we will name that diastereoisomer as trio with similar groups on the opposite side. Let us take one example. Say this is 2,3-dibromopentane. Now, when it is written in Fisher projection, we find that 2 bromine atoms can be on the same side, 2 hydrogens are on the same side, this is one isomer. In another isomer, the 2 bromine atoms are across, 2 hydrogens are obviously across. So, this isomer is given the configuration as trio, and this configuration is named as erythro. Similarly, we can have this example. This is 2-chlorobutane, 3-chlorobutane 2-ol. In this case, we find that these hydrogens are common, whereas these methyls are also common. But let us concentrate on these hydrogen when it is written in the Fisher projection. When the 2 hydrogens are on the same side, this is the erythro configuration, erythro isomer, and when these 2 hydrogens are across, this is trio isomers. So, this nomenclature is used to assign the configuration for different type of compounds, such as even if we have substituted carboxylic acid like this, this is 2,3-dihydroxybutanoic acid. If the 2 hydroxyls are on the same side, this is erythro. Now, again these are 2 enantiomers, the mirror image non-superimposable, and they are assigned configuration according to RS system as 2R3R or 2S3S, but a very simple nomenclature we can define as erythro 2,3-dihydroxybutanoic acid, but both are erythro, remember. So, if we further want to differentiate between the 2, then we will have to use along with that the nomenclature as capital D or capital L, because this will be assigned capital D configuration and this will be assigned capital L configuration, and this is trio 2,3-dihydroxybutanoic acid. So, this trio and erythro nomenclature is used for writing the configuration for compounds which have 2 asymmetric carbon atoms and at least one common substituent on them. Now, after this we will talk about that how the cyclic structure of glucose was arrived at. You see, when different reactions of the glucose were studied and on the basis of certain reactions a open chain structure was given to glucose that we have discussed just before, and then after that Fischer also gave a particular configuration to that structure. Now, based on these reactions, the structure was given that molecule can be reduced to normal hexane. It shows the presence of aldehyde group because it forms an oxime. It also forms an oxazone. Presence of 5-hydroxyl group is confirmed on the basis that it forms a pentaacetate and so on. But during this work, certain reactions were also observed which cannot be explained by this open chain structure. For example, that glucose forms oxime, it also undergoes the addition of HCN, indicating the presence of aldehydic group or indicating the presence of a carbonyl group. But glucose does not undergo 2,4-DNP test, which is considered as the basic test for all carbonyl compounds. So, it does not form any colored precipitate when treated with 2,4-dinitrophenylhydrazine. It does not give Schiff's test. Although we use this test to differentiate between aldehydes and ketones, and with Schiff's reagent a pink color is obtained, but D plus glucose does not give this Schiff's test. It also does not react with sodium bisulfite to form the addition product. So, actually these are the basic tests which are given by aldehyde groups. So, glucose gives some other test, but not these tests. So, in what form this aldehyde group is present, so that some tests are given and some tests are not given. Similarly, the pentaacetate of the D plus glucose, it does not react with hydroxylamine. You remember I said that the presence of 5-hydroxyl group in glucose were confirmed by the formation of a pentaacetate, and we can get pentaacetate if 5-hydroxyl groups are there, and the 6 carbon has got the aldehydic functional group. If the pentaacetate is formed, it does not form the oxime, but if it is glucose only, it forms the oxime. So, what happens during the pentaacetate formation, that aldehyde now is not showing the oxime formation. This was the believed to be the structure for pentaacetate. So, aldehyde should be free. So, what has happened to it? Now, when these studies were being carried out, one more thing was observed, that glucose can exist in 2 different crystalline forms. One form was obtained by the crystallization from aqueous solution at 303 Kelvin. This form is called alpha form and it has the melting point of 419 Kelvin. Then another form was obtained by crystallization from glacial acetic acid at a temperature higher than 373 Kelvin. This was given the name as beta form and it has the melting point of 423 Kelvin. Means when different solvents are used for the crystallization of glucose, we get 2 different forms of glucose in the solid state. One is called alpha form, other is called beta form, and they differ in their melting points. These 2 forms also differ in their specific rotation. The specific rotation of the alpha form was found to be 112 degrees plus, and for the beta form it was found to be plus 19 degree. So, here we find a large difference in the optical activity of 2 different forms. And one very unusual thing was observed here, that when the aqueous solution of any of the above 2 forms is kept for some time, then its specific rotation changes to a final value of plus 52.7 degrees. This phenomena is known as mutarotation. Means what happens, if we make the solution of alpha form of the glucose in water, initially it shows the specific rotation of 112, but when this solution is kept for some time, with the time what we find that its specific rotation is decreasing, and it decreases till the value reaches to plus 52.7 degrees. Similarly, when the solution of the beta form is made, initially its optical activity is measured and it is found that specific rotation comes out to be plus 19 degree, but slowly and slowly it increases, and after some time it reaches to a equilibrium value of plus 52.7, And this was a new thing observed, because till now it was considered that specific rotation for any substance is fixed. How does it change with time? One. And second thing, that why in both the cases, whether it is the alpha form or beta form, we are getting an intermediate value. So, after studying this thing, a cyclic structure was arrived at for glucose. Let us briefly revise this, the definition for mutarotation. That mutarotation is defined as the change in the optical rotation when aqueous solution of an optically substance is kept for some time. We give this definition to mutarotation, and process of mutarotation can be fastened by adding a small amount of acid or base as catalyst. And this mutarotation and some other properties which I discussed before, they showed that D plus glucose, they are different in solid state, but reach to an equilibrium mixture in solution state. Now, one more property was observed. D plus glucose reacts with alcohol in acidic medium as aldehydes react. Now, you know that aldehydes react with alcohols in presence of a small amount of acid as catalyst to give the compounds which are called hemiacetals. One molecule of alcohol reacts, it adds on to this carbonyl double bond, H goes to oxygen and then OR part goes to oxygen, and we get this type of structure where one ether linkage is there and one hydroxyl group is there. We call these compounds as hemiacetals. These hemiacetals further react with another molecule of alcohol in presence of acid, where they involve the loss of a water molecule, H from here and OH from alcohol, and giving a diether type of structures which are called acetals. So, aldehydes react with two molecules of alcohol to form acetals, with one molecule of alcohol to form hemiacetals. Hemiacetals can be hydrolyzed back to aldehyde and alcohol even in presence of water. That is, when they are treated with excess of water or slightly heated, we get back this aldehyde and alcohol, means they are not very stable. But if we want to cleave back the acetals, then we need the presence of some acid. So, acetals undergo the cleavage back to hemiacetal and then to aldehydes when they are heated with water in presence of some acid. So, this was one thing that we know already as a property of aldehydes. But when glucose was reacted with methanol in acidic medium, we obtained a product which was given the name as methyl D-glucoside, but it was found that it contains only one methyl group, but it shows the properties of acetal. So, if it is reacted with one molecule of methanol, it should show the properties like hemiacetal, but it actually showed the properties of acetals. Means when these derivative which are named as methyl glucosides, they are treated with water, they do not get hydrolyzed. They get hydrolyzed only when they are treated with water and some acid. Second thing, that it is not converted back into D plus glucose on treatment with water, but it requires the presence of acid, as I said before, and it indicates that D plus glucose is probably already present as hemiacetal. Since it has reacted with one molecule of alcohol, has given a product that is behaving like acetal, it means glucose already is present as hemiacetal. This was a probable conclusion which we draw from the above observation. Furthermore, not just one but two monomethyl derivatives of D plus glucose are formed. When this methyl glucoside which was obtained was analyzed further, it was found that it is a mixture of two compounds, and these two compounds were separated, and one was having the melting point of 438 Kelvin and specific rotation of plus 158 degrees. This was called as methyl alpha D glucoside, and the other was with melting point 380 Kelvin, a specific rotation of minus 33 degrees. It was called methyl beta D glucoside. These glucosides do not undergo mutarotation, they do not reduce tolerance or failing solution. Means further confirming that these methyl glucosides, they do not contain an aldehyde group, and also they are not present as hemiacetal, because had it been hemiacetal, then it will open up in presence of water. So, based on this, a cyclic structure for D plus glucose was proposed. Now, how this cyclic structure is formed, how the properties are explained, let us discuss briefly here. It was said that from this chain of the glucose, one of the hydroxyl group, here we have shown the hydroxyl group at position number 5, it acting as alcohol attacks this aldehyde group, and this pair of electrons shifts to oxygen, and one of the hydrogen from here goes to this oxygen, it becomes OH group. Means glucose itself forms the hemiacetal type of structure, in which one of the hydroxyl of the glucose itself is involved, and it adds on to this C double bond O of the aldehyde group. Now, if the addition occurs across the C double bond O, originally this C1 carbon is sp2 hybridized and this part is planar. Now, when this ring is formed, this hydroxyl may come on this side or it may go on this side, because now this carbon will also become asymmetric carbon atom, like here it is shown. This becomes a new asymmetric carbon atom because it has got now 4 different groups. One is H, one is OH, that has been formed from this C double bond O. The third is the oxygen, which is the part of the chain, and then fourth is the remaining part of the molecule, which is added across this. So, a new asymmetric carbon atom is formed. So, obviously 2 enantiomers will be formed at this carbon, but overall configuration for the remaining part of the molecule is not changed. So, these 2 molecules which I have written are not enantiomers of each other, they differ in the configuration at carbon number 1 only. The configuration at the remaining carbon, they remains same. So, another term is coined here, we call them as anomers. This term is mainly used in carbohydrates, and after the cyclization, the new asymmetric carbon which is generated, we call it as an anomeric carbon. The compounds which differ in their configuration at the anomeric carbon, they are called anomers. So, one which has the hydroxyl placed on the right side is called the alpha form, and one which is placed hydroxyl on the beta left side is called the beta form. So, actually these were the 2 forms in which the glucose itself is obtained in the crystalline state when crystallized through different solvents. This is the alpha form, this is the beta form. Now, what we observe here, that this is the definition written, that pair of isomers which differ in the configuration at the newly formed asymmetric carbon atom after cyclization, they are called anomers, and this term is mainly encountered in carbohydrates only. Now, it has been confirmed by the various studies that it is the hydroxyl group at carbon number 5 which reacts with the aldehydic group to form a 6-membered ring structure, which is also called a pyranose structure. This name is derived from the name of a 6-membered heterocyclic compound containing oxygen named pyran. This is a 6-membered organic compound, cyclic compound, in which 5 carbons and 1 oxygen is present in the ring. This compound is called pyran. So, based on this, the name to this cyclic structure was given as pyranose, because there is 1 oxygen and 5 carbon forming the ring. So, as you remember, we had earlier discussed that these aldose, that is aldehyde group named as aldose, then we add the number of carbon atoms, that aldopentose, aldohexose, and now in the same way we are adding the ring size. If I am saying the pyranose, it means there is a ring size of 6 carbon atom, but now I will not use the word aldo because aldehyde group is gone, only then this cyclic ring structure has been formed. So, this way we can write now the name as D plus glucopyranose. Earlier we were calling it D plus glucose the cyclic structure. Now, the cyclic structure, if hydroxyl group at carbon number 5 is involved, there are 6 atoms, 1, 2, 3, 4, 5 carbons and 6th is oxygen. So, we call now it is D plus glucopyranose. This is the beta form, this is the alpha form. Now, these corners as written here, do not get confused by these corners, they are not representing any atom, because normally whenever we make a corner in organic chemistry, that indicates as if one carbon is there. Here in carbohydrate chemistry, these are just used to show the linkage, that carbon number 1 is now linked to this oxygen and this oxygen is further linked to 5, carbon number 5. So, these are just the linkage is shown just to show a planar structure, it is not having any carbon in between. Now, if we look at this structure, we can get the idea about the pentaacetate also. We observed that pentaacetate does not give the tests of aldehyde. Actually, what happens when we are trying to acetylate in acidic medium, the D plus glucose cyclizes and it is this cyclic form, maybe alpha or beta, these 5 hydroxyls group 1, 2, 3, 4 and 5, they get acylated. So, what happens actually, we were counting the 5 hydroxyl groups which were forming the acetate were these starting from carbon number 2 to carbon number 6. But what happened that hydroxyl group at carbon number 5 is now no longer available, it has added on to the carbonyl group, but a new hydroxyl has been generated at carbon number 1. So, total number of hydroxyl group remains 5. So, when it is acetylated, we get the pentaacetate. So, we on the basis of formation of pentaacetate, we say that this molecule contains 5 hydroxyl groups, but these 5 hydroxyl groups were not the actual hydroxyls of the molecule, these are hydroxyl of the cyclic structure. Then next we talk about what would be the structure for methyl glucosides which have obtained, because as I said, when glucose is treated with methanol in presence of HCl, again we get mixture of 2 compounds which were called as methyl alpha D glucoside and methyl beta D glucosides. So, if when hydroxyl is placed here on the right side, we call it as alpha form. So, in place of hydroxyl, if it is this is acetyl type of structure that is formed with methanol, so we also name it as alpha form. So, this is called methyl alpha D glucoside, and with the methoxyl on the left hand side, we will call it as methyl beta D glucosides. Now, as I have been drawing this 6-membered ring structure, till now it was not confirmed that whether this molecule contains a 6-membered ring structure or it is some other hydroxyl of the chain that has formed the ring. It might be even 7-membered ring structure if this hydroxyl is involved, it might be 5-membered ring structure if this hydroxyl is involved in the ring formation. The 6-membered ring structure initially was given or was proposed on the basis, because in nature we find that many 6-membered compounds they occur and they are generally more stable. But later on it was found that ring size in different monosaccharides is different also. Now, as I said that when we draw the structure like this, a planar structure, we get some confusion that what type of these bent bonds are there. So, actually these are not the correct representation for the molecule, even the 5 carbons cannot be present in the straight chain like this, because each carbon is sp3 hybridized. So, angle between this bond and this bond will be 109.5 degrees and not 180 degrees as shown here. So, actually these molecules they exist in the cyclic form, and Haworth gave a method of drawing these molecules, we call that as a Haworth projection. So, let us see how the Haworth projection is drawn. First, if we consider this molecule is in this plane, that suppose my hand is representing the 5 carbons like this, and let us say somewhere here is oxygen. This is the carbon number 1 linked to this oxygen, and then it is linked to some carbon number 5, and then remaining part of the molecule is here. So, this is the plane. So, for Haworth projection we will tilt the molecule like this, right. So, it is the vertical plane like this, we make it horizontal. So, this oxygen which was somewhere here in the ring, it comes here, and in the 6-membered ring structure arbitrarily by convention we have given the position that we will give it as a right hand upper corner for this oxygen. It is like this. So, this oxygen has occupied this position, and this is carbon number 1, it goes here, this carbon number 2 goes here, and so on, and then this oxygen is ultimately linked to carbon number 5. So, we draw this as the basic skeleton for this 5 carbon and 1 oxygen. Whenever we will draw a 6-membered ring structure, this position by convention is fixed for oxygen, and we will count the carbon from right side 1, 2, 3, 4, 5, so on. Then in order to show a correct horizontal position, we make these lines slightly thicker, that shows that it is horizontal. Now, what happens to the substituents? These substituents which were present on the right side, when we have tilted the molecule in the plane from vertical to right side downward. So, what will happen, all those groups which were placed on the right side will go under this plane, and the groups which were on the left hand side will occupy the position above it. Let us see that if these lines represent the groups present above and below. This hydroxyl was present on the right side. So, when the molecule has been tilted in a horizontal position towards its right, so this hydroxyl will go below the plane, means it must occupy this position. So, it is placed here, and other groups, this hydroxyl HOH will occupy the similarly lower position at carbon number 2, 3 and 4, hydroxyl H and hydroxyl, and these groups H, OH and H, O and H up to carbon number 4 will be above the plane. Now, what happens at carbon number 5? When this ring is formed, actually this coils up. In that case, what happens? This CH2OH turns upward, so it occupies the position here and H comes here. So, this is the Haworth projection for alpha form of D plus glucopyranose. Now, you see different parts in the name, alpha indicating that hydroxyl is on the right side at the anomeric carbon. Here in alpha form, the hydroxyl will be below the plane. D represents the configuration at the lowermost asymmetric carbon atom. If this is the hydroxyl involved from 5 carbon, it is from this side, plus that this isomer is dextrorotatory. Gluco comes from the word glucose, and pyran in between is introduced to indicate the ring size, that it is a 6-membered ring structure, as is the case in pyran. So, you must practice of drawing this Haworth projection for some other molecules also. Only thing is that first draw the molecule in straight line, then draw the ring wherever the atoms are involved through hydroxyl, then tilt the ring on the right side and draw the ring like this. Remember that this is carbon number 1 in glucose, but suppose it is fructose, then it will not be carbon number 1, because in fructose the carbonyl is at carbon number 2. So, this will be carbon number 2 and carbon number 1 will be somewhere the substituent on this, and then depending upon the alpha or beta isomer, it will have the position above the plane or below the plane. Remember, again I am repeating, groups on the right in a Fischer projection are down in the Haworth projection. So, whenever we convert a Fischer projection molecule into Haworth, the groups which were placed on the right will be below the plane. Then let us have the configuration for the beta isomer. The beta D glucopyranose, there is no difference in the configuration at these carbon number 2, 3 and 4. Hydroxyl at the 5 is involved for the ring formation. The only thing is that in beta anomer, this hydroxyl is on the left hand side. So, when we draw its Haworth projection, we will find that now this hydroxyl will be above the plane. This is the only difference between alpha form and beta forms of D plus glucopyranose. Now, this is again the Haworth projection is a planar structure. We have drawn a ring in a planar form, but again you have studied earlier in stereochemistry that the 6 membered ring structures, they do not exist as a planar ring structure. They are the puckered rings, and the most stable conformation for these 6 membered cyclic structure is the chair form. So, these 6 membered monosaccharides also exist in their chair conformation, and the chair conformation for this D plus glucose we can represent like this. It is represented like this. This hydroxyl is placed below, but when this, with respect to this oxygen, this carbon is tilted downward, then this hydroxyl occupies the axial position, whereas this hydroxyl and this hydroxyl, they all occupy the equatorial position, and this conformation is quite stable because 3 of the hydroxyl groups are occupying the equatorial positions. You have studied earlier in the conformations that more the bigger groups are in the equatorial position, more stable are the conformations. So, I will not go into the details of the stability, it is just we are concentrating here in the drawing that this D plus glucopyranose, this is the Haworth projection, and this represents the exact conformation for it, where hydroxyl at carbon number 1 is in the axial position and which is going downward. And if we do not draw these thick lines because it becomes difficult to draw, we can draw the planar lines like this. So, all other positions of the groups, they remain same as here. Then the conformation for beta D plus glucopyranose, we can similarly draw. Now, this carbon number 1, when it is pushed downward with respect to this oxygen, then this hydroxyl group will occupy the equatorial position, and this CH2OH also goes in the equatorial position here, and this beta form becomes even slightly more stable than the alpha form, because now all the bigger groups, this hydroxyl and CH2 group, they are all occupying different equatorial positions. So, this way we represent the conformation for these cyclic glucose structures. You definitely need some practice. With the help of some book or with the help of some drawings, you can draw for different molecules and practice these structures. Now, let us explain that how 2 methyl glucosides are formed. You see, when we take glucose, whether we take the alpha form or beta form, this wavy line indicates that this hydroxyl may be above the plane or below the plane, that is whether it is alpha or beta, in presence of acid, because we are getting the methyl glucoside in presence of hydrochloric acid and methanol. So, this hydroxyl gets protonated and then it is lost as water molecule, and what happens, this lone pair of oxygen, it comes here and we get this CO double bond with the positive charge on this oxygen. And now a molecule of methanol acting as nucleophile, it attacks on this carbon and this pair of electron goes back to oxygen. So, this methanol now, because this carbon is at that time is sp2 hybridized, can be attacked by methanol either from this side or from lower side. If this methanol molecule attacks from this side, we will have this position for originally OMe, it loses H plus ion. So, we get methoxyl here and we get the beta isomer, and if it attacks from this side, then we will ultimately get the alpha isomer. So, whether we start from glucose, its alpha ionomer or beta ionomer, that is any of the solid form, and treated with methanol, we will get both the forms. But by changing the conditions, temperature, solvent, etc., we may increase the yield of one of the forms, either alpha or beta, or we may obtain one of these 2 glycosides exclusively. That will depend upon how do we adjust the conditions. Now, as I said that 6 membered ring structure was given on the basis that most of the compounds which have 6 membered ring structure are more stable and they occur in nature, but when studies were carried out, it was found that glucose exists in a 5-membered ring structure also. And the 5-membered ring structures were named as furanose on the basis of a 5-membered heterocyclic organic compound which is called furan. This is furan. This is a 5-membered oxygen heterocyclic compound with 4 carbon and 1 oxygen in the ring. So, compound with a similar type of arrangement of 4 carbon and 1 oxygen in the ring, they were given the furanose structure. The furanose structure for the glucose can be obtained when it is hydroxyl at the carbon number 4 is involved in the ring formation. So, when this hydroxyl is involved in the ring formation, this is carbon number 1, 2, 3 and 4. So, ring is formed between these 4 carbon and 1 oxygen, and at carbon number 4 in the ring, we have now CHOH CH2OH group present as a substituent. So, based on all these studies, it is said that glucose is a mixture of open chain form as well as cyclic structures, and cyclic structures can be 6-membered, and if it is 6-membered it can be alpha form and beta form, and if it is along with 5-membered again it can be alpha form. This hydroxyl coming on the right at the anomeric carbon, that is it comes below the plane, alpha form, and if it goes above the plane, that is it placed here on the anomeric carbon on the left hand side, then it is a beta form. When we dissolve alcohol in glucose in water, so it will be mixture of all these forms present. But when we have a solid state and we crystallize from a particular solvent, we may have one particular structure out of this. Now, based on this, the structure for cyclic structure for the fructose was also given, and it was found that D minus fructose, it exists as a 5-membered ring structure. It is the hydroxyl at carbon number 5 which is involved in the ring formation. It attacks the carbonyl group at carbon number 2, and if this hydroxyl goes on the right side, it is the alpha form. If it on the anomeric carbon hydroxyl is on the left, it is a beta form. Now, remember that anomeric carbon here is not carbon number 1, as in case of glucose or other aldoses it will be carbon number 1. In case of fructose, it is carbon number 2 which is the anomeric carbon, and it has got substituent 1 hydroxyl and one other part which is present there, CH2OH here. Similarly, the ring size for many other monosaccharides they have been given, and we will discuss that how we actually confirm the ring size in our next session, that we will not discuss today. The determination of ring size itself involves a series of reactions. Now, Haworth projection for D minus fructose is written like this. Again, remember from the oxygen, the lower number of carbon, that is instead of 1 in case of glucose, it is carbon number 2 in case of fructose, and it is numbered from this side 2, 3, 4 and 5, they are forming the ring. Carbon number 2 having hydroxyl now below the plane is obviously the alpha form, hydroxyl above the plane is the beta form. Now, after getting this cyclic structure for this glucose, we can talk about the mechanism of mutarotation. We discussed earlier that mutarotation is the property that when the solution of a monosaccharide in water is kept for some time, its optical activity changes. And in case of glucose, it was found that whether we start from the alpha isomer or from the alpha anomer or the beta anomer, we ultimately reach to a particular equilibrium value of 52.7 degrees. Means in one case the value decreases, in one case the value increases, but ultimately value is same from both the cases. So, now we can explain that if suppose we start with the alpha anomer, this is alpha D glucopyranose. Now, this is hemiacetal type of structures, as I discussed, that it is the carbon number 1 which was aldehyde group, this is the hydroxyl of carbon number 5 that has formed a hemiacetal type of structure, and I have discussed that hemiacetals can be opened up even in water. So, what happens when we take the aqueous solution of any anomer, say we have taken the aqueous solution of alpha anomer. So, what will happen? Water will attack on this anomeric carbon and this bond breaks, and one H goes here, this becomes hydroxyl group and it loses back the OH one water and this becomes the aldehyde group. So, this is hemiacetal structure in presence of water being converted into the open chain form. Now, this hydroxyl can attack again on this aldehyde group to form the cyclic structure. Now, this is the planar part. When it attacks, it can attack from the same side to give back the alpha anomer, or it may attack from the opposite side to give us the beta anomer. So, ultimately what will happen when we take the solution of alpha anomer, it is large in quantity. Every time this ring opens and closes, so the concentration of beta anomer will be increasing. The same thing will happen if we start with the solution of beta anomer. The ring will open up to give the open chain structure, then closes, opens and closes, and every time the concentration of alpha form is increasing. And whether we start from this side or we start from this side, ultimately an equilibrium is reached when they have a particular ratio for the alpha form and beta form, and the specific rotation at that time is plus 52.7. So, this way we can explain that why mutar actually occurs. It would not have been possible if glucose had only the open chain structure. Now, after getting this cyclic structure, we can also explain some of the reactions which could not be explained by the open chain structure. What were those? One, that glucose does not give 2,4-DNP test. Now, see what happens, 2,4-DNP test involves an acidic medium. Similarly, Schiff's reagent test involves an acidic medium, whereas when we try to prepare the oxime, we use sodium acetate, the medium is slightly alkaline. So, we have observed that in presence of acid, the open chain structure immediately closes to the hemiacetal type of structure. So, when we add 2,4-DNP reagent or when we add Schiff's reagent, immediately the open chain form gets converted into the hemiacetal form, cyclic form, and there is no aldehyde available to react, and that is why we do not get the positive test. But when we have a reagent involving either a neutral medium or slightly alkaline medium, we have the equilibrium between the open chain form and the cyclic form, and now what happens? The open chain form reacts with the reagent, slowly and slowly it is consumed, more cyclic form opens up, and ultimately we get the test, like whole of the compound can be converted into oxime, or when it is treated with phenyl hydrazine we get ocezone and so on. So, all those reactions which occur in neutral medium or in alkaline medium, they are given by these cyclic structures also. Now, the representation of this glucose or fructose in the cyclic structures in the planar form, that how to draw this ring. We came to Haworth and then to conformation, but there are certain rules for drawing the rings. You see, we will draw the ring from that side, from whichever side the hydroxyl that is involved is placed in the Fischer projection, such as this is for D plus glucopyranose. This hydroxyl at carbon number 5 is placed on the right side and it is cyclized with carbon number 1. So, we will draw this ring from the right side, and this will be the Haworth projection, this will be the conformation. For beta form, similarly this ring is drawn from the right side, this hydroxyl is placed on the left side, this will be the Haworth projection and this will be the conformation. We have discussed this earlier, I am just repeating to stress upon here that in the planar structure from which side we will draw the ring, because Haworth and this final conformation will depend upon that. But suppose we have now this thing beta D minus fructofuranose. Now, this is the beta form. So, this is the anomeric carbon, carbon number 2, this hydroxyl should come on the left hand side. This is the alpha D plus glucopyranose, this is the alpha form, hydroxyl at the anomeric carbon should come on the right hand side. It is placed like this. In both the cases, it is the hydroxyl at carbon number 5 which is involved in ring formation, and in the configuration for both these compounds, this hydroxyl is placed on the right side. So, we draw the ring from right side. But in this case, L plus arabinofuranose it is now the L isomer, the hydroxyl at this carbon which is involved in the ring formation is placed on the left hand side. So, that is why we draw the ring from left side, and for alpha and beta ionomers we will draw the hydroxyl accordingly. So, the ring will be drawn from the left side if it is the L isomer, drawn from the right side if it is the D isomer. It has nothing to do with the optical activity of the compound, because it is dextrorotatory ring drawn from the right, this is levorotatory ring drawn from the right, although this is extrorotatory, but still the ring is drawn from the left. So, in the planar representation we will draw the ring from that side on which side the hydroxyl which is involved in the ring formation is placed in Fischer projection. This is alpha D minus fructopyranose. Now, fructose can form a 6-membered ring structure when the hydroxyl at carbon number 6 is involved in the ring formation. This is beta D fructopyranose, this is alpha D fructopyranose. This alpha and beta, okay, we have hydroxyl on the right and this hydroxyl on the left. But now from which side the ring should be drawn? Because when the carbon number 5 was involved, the position of the hydroxyl was fixed. But when this carbon is involved, the position of hydroxyl is not shifted, because this is not the asymmetric carbon atom. So, for this the convention is that if the compound is levorotatory, then we will draw the ring from left side, and if the compound is dextrorotatory, we will draw the ring from right side. So, this is alpha D minus fructopyranose. This is involving the hydroxyl from this carbon, but this compound is a levorotatory compound, we are drawing the link from left side. This is again a levorotatory compound, whether it is D or L is does not matter now. In both the cases it is D, the hydroxyl on this carbon is placed on the right hand side, but we will draw the ring from the left hand side because it is a levorotatory compound. This is L plus arabinopyranose. It is now a 6-membered ring structure involving this lowermost carbon, which is not asymmetric again, but it is a dextrorotatory compound, we will draw the ring from right side. So, remember this convention that if any of the carbon from the chain is involved in the ring formation where the configuration is fixed, then we will draw the ring from that particular side, which is the direction for that hydroxyl group. But if it is the lowermost carbon that is involved in the ring formation, for which the position of the hydroxyl is not fixed, then for dextrorotatory isomers we will draw the ring from right side, and for levorotatory we will draw the ring from left side. Now, next we come to what are glycosides. I discussed earlier that the acetyl derivatives formed when a monosaccharide reacts with an alcohol in the presence of an acid catalyst, they are called glycosides. Means the monosaccharides are already present as a hemiacetal type of structures, they react with one molecule of alcohol and the structure which we get, they are acetal type. So, they are named as glycosides. Actually, when it is glucose, we use the name as glucoside, but when it is any other monosaccharide, whether it is fructose or any other arabinose, 5 carbon, 6 carbon, 7 carbon monosaccharide, a general term glycoside is given. Now, the other part is known as aglycone and the bond formed is known as glycosidic bond, because this is very important term here, the glycosidic bond we will discuss in the chemistry of carbohydrates many times. So, the sugar part that comes within non-sugar part, it is called glycoside. The bond joining them is called glycosidic bond and the other part is called aglycone, such as this is just in skeleton for any monosaccharide, and this is the hydroxyl at the anomeric carbon. It reacts with methanol. We call this compound which is formed as methyl glycoside. So, this methyl is the aglycone part here, and this bond which is now linking this carbon with this oxygen, we will call this bond as a glycosidic bond. There are many naturally occurring phenolic compounds or other substances which remain in the combined form with different monosaccharides, and all those compounds are classified as glycosides. I have taken one example called as glucovanillin. Actually, it is obtained from the vanilla flower, and in this what happens, it is actually this glucose molecule which is in the beta anomeric form, and it is attached to this molecule which is vanillin. When it is hydrolyzed, we get this molecule which is vanillin, and you know vanillin is a very important food flavoring substance. We call it as a vanilla flavor that we use in cakes, ice cream, biscuits and many other eatables. So, it in nature exists in the combined form with the glucose. Then more than one monosaccharides, when they combine with each other to form disaccharides, the linkage between them is also called the glycosidic bond, and such substances are called again called glycosides. Such as say this is just a skeletal representation of two monosaccharides. One is using its anomeric carbon and other is using the hydroxyl group at carbon number 4. So, when they react, so this hydroxyl is acting as alcohol, this hydroxyl is as hemiacetal, and they form an acetyl type of structure. So, this part is now a glycone part, that is represented by A, and this is a glycone part, and this is a glycoside. Now, it has one hemiacetal carbon open. There is a possibility that two monosaccharides may use their hemiacetal hydroxyls, that is present on the anomeric carbon, and they may form the glycosidic bond here. The two are now called as glycosidic parts both. There is no aglycone because both of them are using their hemiacetal carbon structure. So, we will discuss in our next session when we discuss the structure of disaccharides, that how these monosaccharides are linked in different disaccharides, and these type of bonds are called glycosidic bonds. So, we will quickly summarize what we have done today. That first we revised what we had done till now in carbohydrate chemistry, then we discussed about the cyclic structure of glucose, we discussed how these are drawn in the Haworth projection, what are their conformations, then we discussed the cyclic structure of fructose, we discussed the mechanism of mutarotation, how monosaccharides are represented in planar structures, that from which side the ring is drawn, and finally we discussed about glycosides. So, we will continue with the structure of disaccharides and polysaccharides in our next and the last session on carbohydrates. Thank you.
With this note, thank you sir. Thank you so very much for giving us another session on carbohydrates. As Dr. K.K. Arora himself said that we would be conducting one more lecture on carbohydrates very soon. So, dear friends, keep watching us, and if you want to access this particular lecture, definitely you can access us with the help of YouTube, as very soon we are going to upload this lecture on YouTube, and other two lectures on carbohydrates are already there. So, if you want to see them in chronology, there is all for you. So, till then we would meeting again next time. Take care. Goodbye. Thank you sir. Thank you so very much.